So Matt, whenever you're ready, you can get started.
Okay, good afternoon, good morning, everyone. Whatever is most appropriate. Are there sort of questions that came up in the last 24 hours for me?
I guess I had a quick question about the first research question, in that to what extent has it been studied? So
this is the research question that I posted on the order polytope of a polytope.
Yes.
So I'm not sure what's known about this. That's in part because that's part of the reason why I posted it. I guess. So I can tell you what's known simply because the face lattice of a polytope is graded. So whenever you have a graded poset, then the order polytope or the order polynomial has a nice structure. In fact, we'll see a little bit of this today. So when this happens, if and only if the H-star polynomial that I very briefly defined yesterday and we'll talk about today again is symmetric.
Okay.
So, but that we know just because the poset in this case is graded. But my hope was sort of like that you can tell something about the face lattice, from the order polytope. So yeah, like I said in my lecture yesterday, my problems are kind of like somewhat open-stated problems.
I was interested if it would be interesting to consider maybe we take a Metroid Polytope, and so there's an additional structure on the.
So by Metroid Polytopes, you take the indicator vectors of the bases.
Right, and then you take the condensation.
Okay, so you take the indicator vectors of the bases, and that's your polytope. And then you take the face lattice of that polytope.
Right.
Yeah, maybe that's a starting point. So if you're interested in Metroid Polytopes, I will post another research problem. So I guess that will be a research problem number 3. I will post another research problem about a variant of, sort of like an oriented Metroid variant of a Metroid Polytope. Okay. And again, I don't think that has been studied, and I think it's interesting. Maybe I can tell something general about Nick's question, and that is you can try to come up with, so you meaning like anyone can try to come up with interesting polytopes by just taking some structure and trying to take a convex hull. Yeah. So maybe I'll do a blank page here. So in his case, he has a bunch of so he takes bases of a matroid. Bases of some matroid, whatever that is. Okay, so if you don't know what that is, just think of it as some finite structure. Yeah, so a matroid is something that's defined on some base set, and a basis is just a special subset. Yeah, and let's say you have a matroid on n elements. Yeah, and so it's a classic situation where you now can say, okay, let me translate each of those. Each basis is now a 0-1 vector. By telling you just, zero, it's just one, so so sorry, this is a 0, 1 vector in n dimensions. So so for a basis, you have to tell me which elements form a basis. So this is a 0, 1 vector. So now let's take the convex hull. So this is a 0, 1 polytope. So it's a polytope whose vertices have coordinates 0, 1. And often you do this sort of construction and nothing interesting happens. And sometimes you get lucky. And so it turns out, so Metroid Polytopes are super interesting. And that's probably partly why Nick brought them up. And in fact, there's a conjecture in my world, in the Erhard theory world, that says Metroid Polytopes are a class of polytopes for which the Erhard polynomial coefficients in the standard basis are non-negative. That's an open conjecture. And these kind of non-negativity questions are hard, I think. Although if somebody's interested in them, I can give you some pointers. So this is a nice general construction that you can try to do with any combinatorial sort of object. And so so you will see at some point today, I'm writing this up, I have another research project where you do something similar with either the circuits or the co-circuits of an oriented matroid. And I believe people have not looked at that. So in that case, you have a 0 plus minus 1 polytope that somebody should study. Or there's another construction where you can well, there's sort of a general construction that many of you have seen, is where you take a polynomial in several variables and look at the support of this monomial. So by that I mean the exponent vectors, because it's in several variables. There's now a vector of exponents that appear in your polynomial with non-zero coefficients, and you take that convex hull. It's called the Newton polytope of the polynomial, and again, it's a super natural construction and very interesting. And so maybe I should have started there. But one can modify that too, and there's a recent paper that I might or might not extract a research problem out of it for this week, where you take where you do something similar. You look at, these are not 0, 1 vectors necessarily, but they're sort of vectors that sort of naturally appear from some combinatorial situation. And then let's say, let's make a polytope out of it and see what happens. Other questions, either from yesterday or just in general. Okay, so I announced yesterday you're going to get a crash course in Erhard polynomials today. So just like yesterday, well, okay, today we're going to be a little bit more concrete than yesterday. But just like yesterday, I only have 90 minutes, which is too too many minutes to begin with. But so yeah, so my goal is just to show you some structure and some results, and maybe a hint of a proof of some things. And really the idea is, like, if you want to know more, do some of our exercises, or you start reading more. And if, I should have said this yesterday too, if anybody's interested in some, it doesn't matter how specific your question is, or so just a general question, whatever. Is there, whatever. I know the McMahon-Master theorem. Is there a role of this theorem in the polytope world, or something like this? Just don't be shy. You don't have to even ask questions like this in a lecture. So I'm on the Slack channel, and so just very general terms. Don't be shy. And it can be big questions or little questions, or so it can be something very, very specific or something very vague. And in both cases, I'll try. Can't promise that I know the answer. Okay, so yeah, so so what are we doing? So we're going to start with a lattice polytope. So lattice polytope. Yeah, let's say P. Yeah, so this means this is the convex hull of integer points. Yeah, so I typically maybe write the vectors in my convex hull description as a matrix. Yeah, so this V. So in my case will be an integer matrix. Yeah. And so let's say I live in D dimensions and I have n vertices. And as we said yesterday, so there's a dual description of a polytope as a system of a solution set to a system of linear inequalities. Yeah, and so so lattice refers to this choice here. So it refers to our vertex description, and then you can realize, okay, in the so over here you can realize that the the matrix A and B. So if you have integer vertices, then they have to have rational coordinates, and you might as well make them integral. So they have integral integer coefficients. But this does not mean that my vertices are automatically integer vectors. So it goes in one direction. Yeah, and so again, so we started with this yesterday. So what I'm interested in is the Arrowhead function. Yeah, and so yesterday I started to motivate this by a volume problem, and so I'm counting, grid points as I'm making my grid finer and finer. But we can also think of dilating the polytope, and so counting integer points. And so, as many times in combinatorics, it's convenient to encode this in a generating function. So for reasons that I will tell you about in a moment, I'm going to declare this generating function to have constant term 1, and then I take I take these counting numbers and stick them into a generating function. So this is a single variable z. And so, maybe we'll do sort of a running example. And this is actually this is on the exercise. So, I'm not going to give proofs, but you can think about that. So the simplest possible sort of lattice polytope is what's called a unimodular simplex. So this is the convex hull. So in general dimension, I should say, so this is the convex hull of the origin and the unit vectors. So E1, E2, ED. And so I claim, so if you think about this, so the inequality description is, well, every coordinate has to be bigger than or equal to 0. And then there's sort of like this one non-trivial inequality. And so, so this suggests that the Arrowhead counting function is, you can think of directly from this description. Sorry. So this is for my simplex here, delta. So what are we doing? We're counting now integer solutions, right? Everybody's still bigger than or equal to 0. And then, dilation by n just means that your equation over here is going to get a less than or equal to n over there. And so you do some sort of basic combinatorics and realize this is a binomial coefficient. N plus d choose d. And there's other ways to derive this, but if you now go over here and compute this generating function with a binomial coefficient, then so there's your friend, the binomial series helps you, and you realize in this example, this evaluates to the rational function 1 over 1 minus z to the d plus 1. So this is the sort of data to play with. Are there any questions on my definitions or on this example? Okay, so okay, but how, what sort of like constructions do you do to compute these quantities? So an important construction is what you see in this picture over here. So I like to call this the homogenization of my polytope. So let me draw a picture first. So I'm thinking of my a given polytope as this this pentagon over here. So this lives in 2 dimensions. I guess this is not a vertex. sorry, this lives in 2 dimensions. Okay, and so the homogenization is I take my vertices, so still think of this as a matrix, and stick a bunch of ones up on top. So each vertex of the polytope now gets lifted 1 dimension higher with a 1 on top. So I guess maybe we shouldn't call this the x0, the x3 coordinate, but the x0 coordinate. Yeah. And now I take the non-negative span of this. Yeah. So my notation over here just means take linear combination of your column vectors with non-negative coefficients. This is a cone, a polyhedral cone, and it's the cone, it's this 3-dimensional cone that you see in my picture. Yeah. And so, so the reason why I like to call this the homogenization is because there's an easy way to think about it from the half-space description of your polytope. So so what happens now is you're in D+1 dimension, where I think of sort of my vector up on top. Come on, you can erase it. I can think of my vector up on top as like, x1 through xd. And so now I'm adding, I'm adding an x0, so this will be just a scalar in front of this vector b. So, or if you prefer, you can rewrite this system over here, by bringing the b vector on the other side. So I have, sort of a matrix, negative b times the matrix A times now a d+1 dimensional vector x less than or equal to 0. Just give me 1 second. Sorry about that. Yeah, so you can see I'm defining a cone here. And in my picture, you can sort of see why this is interesting. Yeah, so if this here is P, then my big cone is, Hom of P. Yeah, and so what happens now if you intersect this cone with sort of a horizontal hyperplane? Yeah, so Hom of P intersected with a hyperplane where x0 is equal to n. Yeah, so you essentially see n times p. Yeah, so I mean, really what you see is n times p, cross n, right? But okay, who's counting? Yeah, so the, if I'm interested in dilations of my polytope, then Hom of P is your friend. That's Hom of P contains, this is a cone that contains all positive dilations at the same time. Okay, and so if you now want to understand the sort of integer point structure in dilations of your polytope, this should somehow be encoded by the all integer points in Hom of P. So every integer point in Hom of P belongs to exactly one dilate. And so so what you want to study now is what I like to call the integer point transform of a cone, actually. Or really it's really any set. So but let's just think about this set as living in D+1 dimension, because in a moment I want to compute the integer point transform of Hom of P. It's a multivariate generating function that captures everything, that captures all the integer points in S. So let's call this sigma sub S. So this is a multivariate generating function. So maybe let me use variable Z1, C naught, C1, and so on down to ZD. So what I want to capture is all integer points M in S. So all points M in S with integer coefficients, and I encode every point as a monomial. So C naught, M naught times C1, M1 down to ZD, MD. So this is a funny way of listing all the integer points in your set S. And so if your set S is some crazy set without structure, then can't really do much with that. But in our case, the set S is a polyhedral cone, and it turns out you can write this crazy list in a nice way. Let me just introduce some abbreviation. So I'm going to write this as sort of a vector Z, and if it's not clear that I have a vector, then I'll do a little bar underneath. And so we're going to write this monomial as a vector Z to the exponent vector M. And so when I say vector Z to the vector M, I mean this monomial. Are there any questions about what's on this slide?
So this polynomial is just the sum. We are not considering any other possible function made of these monomials.
Yeah. So right now, think of this as a formal power series or formal Laurent series, right? Some of your exponents might be negative. So it's a formal Laurent series. It's just a formal sum of these monomials with, like you said, coefficient 1.
Mm-hmm.
Think of it as like an indicator generating function where your indicator function picks up exactly the integer point in some set S.
I think there's a question in the chat. I'm not sure if you can see it, Matt, because your screen.
I can. So I appreciate, Max, if you could tell me.
Yes. So Hom P is also called the cone over P, right?
Mm-hmm.
Okay, that's what I thought, but wasn't sure.
Yeah, yeah. The reason why so when I was younger, I would also like to call this cone of P. The reason why I prefer Hom of P is because cone of P can mean different things. I mean, just to give you a picture. So if you're in two-dimensional, so I'm going to draw a two-dimensional picture, and here's your P. It's completely reasonable to call this the cone of P. So this is a two-dimensional cone, yeah. And so yeah, so to avoid not being clear, I prefer Hom. But we can still be friends if you call this the cone over P. Okay, so why? I'll do an example in just a moment. Yeah, but why are we doing this? Well, I claim so the Erhard series of P is in here. So let me write down first where you can find the Erhard series, and then try to convince you that this is correct. So here's what I'm just going to do is I'm going to take the Hom of P. I'm taking the integer point transform, and now specialize at single variable z, comma 1, 1, 1, 1, 1. So if you've never seen this, this is a bit fast, but let me give you a picture anyway. So the Hom of P is this cone that you see a picture of up on top. And so now I make up my generating function in several variables. And so this generating function just picks up a bunch of integer points here, and then here, and here, and so on. So okay, lots of integer points. And with this specialization now, so the sigma function now, first of all, just every integer point is equal, right? So every integer point gets listed exactly once as the exponent vector of some monomial. But now I'm going to set a whole bunch of most of the variables, namely these ones down to here. I'm just going to set them equal to 1. And so in terms of your monomial, that really means I'm going to ignore the m1, m2 through md coordinate of your point. Correct? I'm gonna move them all together, and I will only keep track of it will only keep track of the m0 coordinate, which is your height. And so if you think about this for a moment, so what you're now going to get is you're going to sum together, all these ones. You're going to sum together that have the same m0 coordinate. And so the m0 coordinate tells me how high I am in my cone. And so you can think of this as so this m0 coordinate really corresponds to the dilation, correct? This is what we're saying up here. So in other words, if you have a magic box that can compute integer point transform of cones, you can compute Erhard series. So that's one way that people compute Erhard series in the real world, actually. All right, let's do an example. Yeah, so let's continue with my running example. Yeah, so yeah, so this was my unimodular simplex. Yeah, so we had convex hull of the origin and then the d unit vectors. So okay, so here's the recipe, right? So let's compute the hom of this. So this is the cone generated by, so let me now write this as a matrix, right? So you have a bunch of ones up on top, and then here are your vertices, right? So I have the origin, and then I have 1, 0, 0, 0, and so you see sort of like this. There's a whole bunch of zeros here, and there's a whole bunch of zeros here, and you see a 1 in the diagonal. Yeah, so everybody with me? Okay, so today you really have to yell if something's not clear. So okay, so let's compute the integer point transform of this. So this is okay. So this is multivariate. Okay, so z here is multivariate. Okay, how could we do that? Well, it turns out there's a reason why I'm choosing this example, because this matrix is super nice, correct? Yeah, so these columns they form not just a basis, but a lattice basis. Of z to the d plus 1, right? So this usually doesn't happen, right? So if you have a d plus 1 dimensional cone, so with d plus 1 generators, okay, if those vectors are linear independent, they will form a basis of r to the d plus 1. But in this case, I have something much better. And I have there's a reason why the simplex is called unimodular. So this has determinant 1, and so this actually forms a z basis of the integer points, correct? And so what does that mean? That means every, right? So that means every integer point now, this is what we are interested in, right? Every integer point in this cone is simply, right, some, sorry, I should have said r greater than equals 0. And every integer point is a unique, maybe I'll just write it like this, right? So it's a unique non-negative integer combination of my vectors. And so that means my generating function is of a very special form, right? So if you now think of this as, building up from geometric series, you're going to see like a 1 over 1 minus c naught. So this comes from so this comes from the first generator over here. So the first generator has a single 1 in the 0th coordinate. So the next one is a 1 minus z naught z1. So what you see here is the second generator, right? So I have a 1 1 and then the rest is 0. So I'm building up monomials that correspond to these vectors, to these generators, and so on. So each generator is going to have give rise to a c naught, because that's my 0th component, and then one more coordinate, and this one more coordinate runs. So if you think of, each of these factors, you take 1 over each factor as a geometric series, and then start multiplying out, you're going to get exactly the integer combinations. So so general sort of cones are not that nice, but in this case, I'm lucky. So you get this very compact form of this integer point transform of this infinite formal power series in n+1 variables. And so, okay, so let's specialize. So if I now keep the first variable, but I'm going to set the other ones equal to 1. Lo and behold, I get 1 minus z, 1 over 1 minus z to d plus 1. So we already discussed that this was the Erhard series. Are there questions about this example?
So is this specialization the analog of graded Hilbert series versus multi-graded Hilbert series?
Mm-hmm. Did you say Hilbert series?
Yeah.
Yeah. So I was going to talk about this on Thursday, but maybe I can give you a preview about these terms. So there's an algebraic structure here. Okay, I have 2 minutes. Let's try. Okay, so what's the algebraic structure over here? So if you start with a polytope, lattice polytope, really. Then I'm going to form this cone. And so like we said, really I'm interested in the integer points in this cone, right? Then this forms a semigroup. So this is just a fancy way of saying, you take 2 points in there, and if you add them, you stay within the set. So if you want to impress your friends, you say that's called a semigroup. And so, what you've seen this in Martina's lecture yesterday. So what you can do now is when you have a semigroup like this, so this is a sub semigroup, I guess, of z to d plus 1. You can form a semigroup algebra, let's say over C. So so what is this algebra? Well, it's the algebra. It's generated precisely by the monomials in my integer point transform. Right? So it's precisely generated by all. So these are now vector. These are monomials in d plus 1 variables, let's say over C. So if you had, if my Helm of P was not a cone, but was something finite like polytope, then you would generate finitely many polynomials, but you're going to have a hard time creating a semigroup out of that. That's why I'm doing the Helm. And so in this language, my integer point transform is what's called the fine, sorry, the multigraded or the finely graded Hilbert series of this semigroup. Multigraded Hilbert series. And so, so if you want to, so if you want to now, out of this, if you now want to get sort of like a one variable Hilbert series out of it, and that means that you have a linear functional by which you grade. So this is really now an evaluation. So you go through, you do a special evaluation of my vector z. And sort of in general, what you want to do is you want to have a single variable. Maybe let's not call it z, but let's say something x to some power, a0, and the same x to some power a1, and so on, and down to a d. So this, my a is now an integer vector, okay, and this gives now a what we would just call a Hilbert series, or sort of a one variable Hilbert series. And the Erhard case is the special case where my vector a is 1, 0, 0, 0. It's not the only interesting case for a single variable grading, but it's the one that I'm interested in when I want to do this Erhard, stuff. So yeah, so good question. We'll talk a little bit more about this on Thursday, because on Thursday I want to do. On Thursday, actually, I want to show you some of these things that you can't quite do with polytopes. So I want to show you what sort of happens in sort of slightly more general scenarios. But yeah, so if you have a magic box that can compute multigraded Hilbert series, then we're good. Yeah, you can compute Erhard polynomials.
Thanks.
Other questions before our coffee break?
Yes, I have a question. So in this example, we had a matrix, a very nice matrix, and it was easy to find the sigma function. So in general, are there conditions like if this matrix is generates the columns generate the R as zeta bases, then we can always do this?
Yeah, so we'll talk. So I think I understand your question, but tell me if I'm not answering it. So we'll talk about this after the coffee break. I give you a very, very quick preview here too. Yeah, so this is sort of a two-step process in general. Yeah, so you can ask, okay, what if I don't have a simplex, but I have some polytope? Yeah, that's already a different situation, because now the hom, so the cone over this polytope, right? So my hom is not simplicial. I have more generators than the dimension, right? So I not only did I, like you said, Jonathan, I needed this matrix to be unimodular, but also in particular, I wanted to be a square matrix, correct? So otherwise, I'm in trouble. Yeah, and so already this is not true for a general polytope P. So this is where triangulations come in. So for a general P, I'm going to triangulate either P or the hom. Yeah, and so we'll talk about this tomorrow. Yeah, what that means in terms of these counting functions. Yeah, and so now I'm in your situation, right? So now I have a Hom over some simplex S. Yeah. So this is now a simplicial cone. Now I have a d+1 by d+1 matrix. Yeah. But so now the question is, what do you do when this is not a unimodular matrix? And that, we'll talk about after the coffee break in a moment.
Okay, thank you.
All right, let's take a break. Yeah, so let's for this last sequence. This has nothing to do with Ehrhart polynomials. Yeah, so once you stick a polynomial of degree d into a generating function, it evaluates to a rational function for which we know the denominator. It's 1 minus z to the degree plus 1. And so, so I guess this is for some, polynomial h star of degree less than or equal to d. And so my notation here is not an accident. So out of this, I claim that h star polynomial is exactly the coefficients in the basis that I mentioned yesterday. So when you write, so this is just a translation of this rational function in terms of a power series. So if you write in the Ehrhart polynomial in my third basis yesterday, so this is n plus d, choose d, down to, I guess the last one was n choose d. So this was my basis number 3. Then those coefficients are the coefficients from this numerator polynomial. And so if you hear the word h star vector or h star polynomial, this is what people mean. And I already mentioned this yesterday. So there's a, one of the more famous theorems of Stanley says that, so this is, I think in 1980, this says that these coefficients are non-negative integers. So today we know some, fairly not too bad proofs of this theorem. Back in 1980, this took some serious work, and in fact, it used some commutative algebra that you see in Martina's lectures. I also mentioned the other bases. So maybe let's write this in orange. Yeah. So I can also write this in terms of the binomial coefficient, basis with n choose 0, n choose 1, and so on. So this is called the f star vector of the polytope. And there's a theorem that really shouldn't be called a theorem, but there's a theory that was developed by Felix Breuer much more recently in a paper in 2012, and I mentioned this in the research project that I posted yesterday. And among other things, this theory gives an interpretation for the f star coefficients, again, they're non-negative integers. So I'm saying this shouldn't be called a theorem because if you write down the relation between h star and f star, you will realize once you know that h star is non-negative, f star has to be non-negative as well. So this is only a very, very small part of this theory of f star polynomials that Felix developed. And so, yeah, there's much more there. You know? There's much more there. Okay. So that's the connection to yesterday. And so, so now, we can start imagining, okay, if, h star are non-negative integers, f star are non-negative integers, that means, hopefully there's a sort of accounting interpretation in there. Yeah. And yeah, so in some examples, this can be done rather easily, and in other examples, you have to work a little more. But there is sort of like, at least in some convoluted way, there's always a accounting interpretation for these coefficients. Okay, let me maybe mention one more thing. And so this is, I will really not stress this much, but there's a beautiful reciprocity theorem here. So this is what's called Mcdonald reciprocity. And it's the following phenomenon. So so this was proved in 1970. It's the following phenomenon that, if you have, if you now know that this function over here is a polynomial, then you can ask, okay, what happens when I plug in things like 0 or negative numbers? And it turns out you're counting something, so up to a factor, a sign that just depends on the dimension, what this is doing is you're counting integer points in the interior of your polytope. So maybe we can see this in an example. Yeah, so our running example of the unimodular simplex. So there we had the Arad polynomial n plus d choose d. And so if we plug in, negative n, so how should we think about this? So this is really 1 over d factorial times sort of a product n plus d times n plus d minus 1, and so on down to, I guess, n plus 1, right? And so, if you now take this expression and plug in negative n in, right? So then up to a sign, you will get the binomial coefficient n minus 1 choose d, correct? Yeah. So if you plug in negative n into n plus 1, you get negative n plus 1, and then you get negative n plus 2, and so on. And so if you take out d minus signs, you get n minus 1 times n minus 2, and so down to n minus d. And Yeah, so if you, so now, maybe this should be, no, I think Max put this on the exercise actually. Yeah, so if you now take this, this unimodular simplex, standard unimodular simplex, and look at the interior, yeah, I claim the lattice point count in n times the interior is this n minus 1 choose D. Maybe let me make one more remark about this, and then, well, maybe two more remarks. So number one, this has a generalization in the world of multivariate generic function in terms of integer point transform. You know, so, this is another important theorem of Stanley. This was in 74. Yeah. Let me not write this down, but you can read up on this. Yeah. So this gives a reciprocity theorem in several variables. So for integer point transforms of rational cones. And if we then do the specialization that we've been doing before the coffee break, you get this Mcdonald theorem. This is one remark I wanted to make. Sorry, Ariaman had a question. F star, yeah. Yeah, so so I'm reacting to the chat, to the question in the chat. Sometimes, so I like the F star bases. Sorry, that's exactly what you meant, actually. You're right. So thank you for this. So I like to write this in terms of n minus 1, choose whatever. And I think only then Euler's theorem is true. Thanks for the comment. But you're also correct that this is just a shift in the argument. Okay. Another reason why I wanted to show you the reciprocity theorems here is they help with our general question, right? So our general question is like, okay, which polynomials are Arrowhead polynomials, for example? Yeah, and so what this suggests now is you have another criterion. Yeah, so take your polynomial and plug in negative n, and up to a sign, then you should get positive evaluations, right? If you plug in -1, -2, -3, I know all these evaluations, they should have the same sign. If not, your polynomial is not an Arrowhead polynomial. Okay, so that was about reciprocity. Okay, so let me give you a little bit of an idea of how one proves this in general. Yeah, so we already said, okay, so if you start with a polytope, so the first thing we want to do is we're going to triangulate. Yeah, so we'll talk about this tomorrow, but triangulate means that I write my polytope as a union of simplices. So if I am dimension D, I want to write my polytope as a union of polytopes with each having D plus 1 vertices. And so now, okay, then I have some simplex, S, and so now I take the hom over the simplex S, correct? So this is a cone. So let's say, so I have some matrix, let's say W, right? And so this, so this W is really, so this is really this matrix coming from the vertices of my simplex, and I have a one on top. And so now, we're saying, okay, if you can understand this integer point transform, then you're in business, correct? So if we understand this, then we're good. And so I forgot the name of who asked this question earlier. So so if my matrix W has determinant plus or minus 1, I can do what I did before. So then you can write down this this integer point transform on the nodes. But sort of the general case is pictured here in these pictures. So let's say I have a three-dimensional cone. That's the last picture I can draw. And I have my three generators over here. But they don't form a Z basis. And so what this picture is supposed to show is you form the what I like to call the fundamental parallel pipette of the cone Hom S. So so this is I'm doing the same construction as when I compute my cone, except now my I'm not sure why I'm writing this parentheses here. So now I'm only taking linear combinations with coefficients between 0 and 1. So if you look at my camera picture in a moment, so I have my three generators in 3 dimensions, and up on top, what I did is I computed, the cone that they generate, so all non-negative combinations. And so now what I want to do is I want to compute just the parallel pipette that they generate. So that means I take only combinations of my three vectors with coefficients in 0 and 1, and I want to make that half open, so I don't allow 1 as a coefficient. And the reason why this is interesting is something you can see over here. So with this parallel pipette, I can now tile my cone. So what I mean by this, so what I'm interested in is this cone, correct? And I'm interested in the integer point structure of this cone. But my parallel pipettes, my pi here, so if I take pi and translate by the right amount, I can tile the cone. And translating by the right amount is, if you think about this for a moment, is precisely all integer combinations of the generators. And I want to make pi half open so that I don't have an overlap. So if you've never done this, you should do one of our exercises. So I claim this integer point structure can be had as follows. First, I'm going to start with the integer points in pi. I'll start here, and now I translate those in all possible ways of translating the generators of my cone with integer coefficients. And so, so the special case where my matrix is unimodular, is I don't know why I wrote this over here, but okay. So that means that that means my parallel pipette has volume 1, and because it's half open, the only thing that's contained in here is the origin. Yeah, and so this is just the origin, and I'm really just I need to consider integer combinations of my matrix W, of my column vectors in W. Okay, and so if you put this together, this gives you now a recipe of computing this integer point transform. So from here, we're going to get the same kind of geometric series before. So I get 1 minus. Let me just write this as z to the w1. So these are my columns now. Down to 1 minus z to the w d plus 1, I guess. And in general, I have to encode these integer points, and well, they get encoded by another integer point transform. And if my only integer point in pi is 0, this integer point transform that you see up on top is the monomial 1. And that's what you saw in the example. So this gives you, I'm going to pause in a moment for questions, but I want you to realize that, this up here, right? This gives you the H star polynomial. So this is a vector z, but by specializing this vector, you leave the first coordinate variable, and then the rest is 1, 1, 1, 1, 1. That gives you H star. And so in particular, so what does that mean? So this means here is the complexity of computing H star. This is where the meat is. So if you cook up a simplex for which the hum of the simplex has lots of integer points in the parallel pipette, then we got a problem, because everything else in my formula here is given by the generator, so we know that. But that's where the computational bottleneck is. So this parallel pipette pi can be large in terms of volume or in terms of integer point count. Okay, I want to hear your questions. This was quite a whirlwind tour here. Either everything is clear or everything is completely unclear. Who wants to ask a question?
So I have a question.
All right, Antonio.
Yes, this is, so you have to do this for every phase of the triangulation of your polytope then, right?
That's a good question, and that's something we're going to talk about tomorrow. So what Antonio is referring to is, so if I now write my P as a union of simplices, right, then I'll do this for each simplex. Let's say I have a magic box that computes all of these things, right? But now if I want to put everything together, then I need to use some sort of inclusion exclusion. correct? Because my simplices, they overlap at least in faces. If I have a nice triangulation, yeah, well, if I have a triangulation, then they overlap in faces. Yeah. But there's some tricks, Antonio. Yeah, so we'll talk a little bit tomorrow about this. So yeah, the way I want to think about triangulations is there's sort of different ways. Well, okay, let's just talk about this tomorrow. So it's a bigger theme. Okay, it's a bigger theme. So there's a way to do triangulation and compute these things without having to do inclusion exclusion. Yeah. You know, you can think of sort of like a half-open triangulation. Sometimes you want to do that. Sometimes you want to do inclusion exclusion because it's mathematically interesting. You know? And sometimes you only want to do exclusion. Anyway, we'll talk about this tomorrow.
Okay, thank you.
It's a very good question, and it fits exactly on the slide because that's part of the complexity, correct? If you know, if the only magic box to compute these things via triangulations is you do inclusion exclusion, and now you have a triangulation that has a lot of pieces, including a lot of lower dimensional pieces to deal with, that increases your complexity. So Antonio is right on asking this question. Yeah? So these are important issues when you think about actually firing up a computer and do this.
I also maybe have a question.
Okay.
Yeah, remember well that is it connected with number theory?
Yes.
You mentioned it yesterday. Yeah.
Yes, there's a lot of number theory here. I can tell you at least one thing that's sort of in these pictures, right? So you can think of this thing here. You can think of this as a torus. Correct. So you can think of this as like a torus picture of your cone. Correct. And so already there you can play some number theory. But there's other number theory that comes in.
I remember something with how was it, Minkowski sum order in number fields or so, for proving that Picard group is finite or so. But yeah, these are.
I'm not sure if that involves polyhedra. Yeah, I'm not sure, but I'm not an expert on this. So the type of number theory I do, and I can give you just like a 20-second spiel about this, is again when you actually want to compute. Yeah, so when you actually want to compute, let's say, an Erhard polynomial of a very specific class of polytopes, you can write down some very simple classes of polytopes, and the computation becomes very hard. And sometimes number theory can help. And so these are sort of mostly analytic methods. So you have sort of analytic number theory that helps here. It has a feel of sort of Fourier analysis. So that should make sense because if you think about sort of your generating function, there's a lot of that's sort of the feel you get. There's sort of Fourier analysis type techniques that are useful here. That can be useful.
Okay. Thank you.
There's one more question in the chat. Is it correct to say that every unimodular simplex is the image of the standard simplex under a unimodular matrix plus a translation, perhaps?
Perfect. That's perfectly correct. Yeah. Yeah. Think of a unimodular simplex as by definition. Okay, so a general unimodular simplex by definition means you're standing at one vertex and you see the edge directions. You see the edges towards the other d vertices. Yeah, and I want this to form a basis, a z basis of z to the d. And as you know, any basis of any z basis can be unimodularly transformed to the standard basis. And that's exactly the map that you're talking about. Okay, I want to spend the last 6 minutes back on the theme. Okay, so this wonderful picture basically tells you everything that we know in general about classification of Erhard polynomials. Okay, it's a little bit of a sad state of affairs, but it makes my life interesting, so I'm not complaining. So you can ask now the very general questions. So which polynomials are Erhard polynomials? So, for example, and this is what this picture tells you, is you have some degree 2 polynomial, and you can ask, can you find me a lattice polygon now, right? That it has your polynomial as an Erhard polynomial. And you can ask the same question about degree 3 polynomials and so on. I guess you can also ask it about a degree 1 polynomial, but maybe that's not super interesting. And so let me give you the answer. So I claim this constant term has to be 1. In fact, this is a theorem for any Erhard polynomial. The constant term is 1, so that's done. Yeah. And the other thing you can sort of prove from the get-go just by looking at H star thing is in dimension 2, these other 2 coefficients, they have to be half integral and positive. Okay. You can say more, but that's sort of from the get-go. Yeah. So this is a necessary condition. So just from the fact that H star is integral and positive, I claim you can deduce that. Yeah, so these 2 coefficients C1 and C2 are half integral. And so here, everybody, meet my picture. This is every possible Erhard polynomial in dimension 2 written as a point. Written as a point C1, C2. So here, for example, you see the point 1/2, 3/2. Yeah, and this, if you unravel this, this corresponds to the Erhard polynomial of our unimodular triangle. So if you unravel this, and so there's now a half, every half integer there's a bunch of points here, and everybody in this gray area over here, and then everybody on this ray up here, and then our very special friend over here. This is the point 9/2, corresponds to a pair of coefficients that appear in an Erhard polynomial, and that's it. It's an if and only if. So the fact that this picture looks kind of funky gives you an indication that this is a non-trivial theorem. So this is basically we know this theorem basically since the mid-70s, even though back then we didn't think about it in those terms. So many of you have heard of Pick's theorem, so that's at work here. So there's in dimension 2, there's not that much that can happen in terms of Erhard polynomial. And then there's another theorem that gives you sort of a bound in special cases. And when you throw all of these things in a pot and stir for a while, this picture pops out.
There's a question in the chat if that isolated point is a Erhard polynomial of anything interesting.
Oh yeah. It is super cool. Yeah, so definitely a good question. Yeah, so this is this belongs to the following triangle. So you go out, you take the origin, and then you go out by 3 in both directions. That's this triangle. And what's cool about this triangle is it has exactly one interior point here. Sorry, one interior integer point. And so, if you're interested in this point 9.5, 9.5, you should do one of our exercises, namely the one on reflexive polytopes. So this is a reflexive. This is a very special reflexive polygon. It's in dimension 2. And it's interesting in the sense that, well, I can tell you a little more. So, I should tell you, which things are on this ray over here. So these are sort of, they must be some sort of extreme polygons. Yeah, on this ray are all polygons with no interior lattice points. So you can cook up. Maybe we should have made that an exercise. Actually, you can cook up realizations of all these half-integral points as Erhard polynomials of lattice polygons with no interior lattice points. And so, everybody else has interior lattice points. And so now what happens is, once you have interior lattice points, there are now new constraints on your Erhard polynomials, with one exception. This is the exception. So there's a bunch of constraints, namely, this constraint and that constraint that you have when you have interior lattice point. So there's a theorem about this, okay? And there's one exception, and it's this beautiful little triangle, over there, reflexive triangle. I'll try to read the chat. There's more things going on here. Yeah, Max is quite right.
So I have another question then.
Yes, Alessio.
So, I mean, this is not a fun, of course, but it seems it is a union of polyhedral cones.
Yes, that's correct.
Is that reasonable? And what do we know about dimension 3?
That's an excellent question. So we can ask, okay, what can you give me a picture like this in dimension 3? So you're right. So I can think of this as a union of polyhedra, correct? I mean, my gray thing is a polyhedron, and then my point is a polyhedron, and then my ray is another polyhedron. So this is a union of polyhedra, and then I can I have to intersect that with the half-integral lattice, but that's sort of a that's just sort of a necessity. So maybe one should draw this picture for H-star for the H-star polynomials, not for the in the other bases, right? Then my constraint is just that H-star lives in my H-star vector lives in some region like this, and on top of it has to be integer. So okay, so we have some union of polyhedra, and then you look at the correct integer structure, and those will get you the Erhard polynomials. We don't have a picture like this in dimension 3. We have necessary constraints. So we know we have a finite union of polyhedra, and we know every Erhard polynomial has to live somewhere in there. But we can't even prove, and I think this is the correct statement, we can't even prove that the final answer, whatever it might be, for the complete classification, is a finite union of polyhedra. So yeah, so this picture gets, in dimension 3, this becomes a 3-dimensional picture. So that doesn't sound too bad, correct? But this picture becomes funky. It becomes very, very funky. And if you want to see some pictures, there's a very nice paper by Gabriele Balletti. So you can look up his papers. He has some recent papers where he, it's basically very, very serious experimental math, where he tries to smartly compute this picture in dimension 3. And so you'll see very, very pretty pictures. Yeah, but so this classification problem is open in dimension 3. And as I said, embarrassingly, we don't even know qualitatively what to expect.
Thanks.
Maybe let me say one more thing, and then we can stop the recording and answer more questions. Yeah. So okay. So okay. What happens now in dimension higher than 2? Okay. We can't draw a picture like this, and so as mathematicians, right? What's the next best thing we do? We say, okay, can you tell me something in special cases? Yeah. And so this is what people have concentrated on. Yeah, so you can ask special cases of classes of polytopes, or you can ask special cases of classes of Erhard polynomials or Erhard H-star vectors and so on. Yeah, so for example, one thing that we know is when is an H-star polynomial symmetric. This basically goes back to reflexive polytopes, which is in our exercises. Yeah. So in other words, the class of all lattice polytopes, in fact, in any dimension, with a symmetric H-star polynomial, they are classified. I can tell you exactly which polytopes there are. And yeah, that's almost it, really, in general. So we can do zonotopes. Sort of, okay. We can sort of do zonotopes. Yeah. So yeah. So by sort of, I would need more time, but yeah. But here's a question you can ask, and already this question is open. When is H-star or F-star unimodal? This probably does not have an answer. That's my guess. Yeah, so this is, we defined unimodality yesterday. And so this is often a question you ask once you have a vector with non-negative coefficients. It's especially a question you ask once you have a symmetric vector with non-negative coefficient. But it also makes sense to ask this question if the vector is not symmetric. Yeah. And so again, yeah, so like I said, already this question is, I think, too hard, because there might not be a nice answer. So again, you can specialize the special question. Yeah, so now we can ask, hey, I'm interested in this class of lattice polytopes, and it's a super nice class. Could it be that H-star is unimodal for that class? And in fact, that's one of the things we know about zonotopes. Yeah? So that's one of the things we can prove, that in that special class, that special question has a positive answer. So anyway, there's lots of there's lots of things. This is a really, really open playing field. And in some sense it's too open. Yeah, so I think the general classification problem here is maybe not the right question, because it might not have an answer. But then you can ask sort of a partial classification problem, maybe for a partial class of polytopes. And this becomes very, very interesting. Okay, well, we're over time, so thanks for the attention today. And of course, my brain is open. We can talk more questions about more questions that you might have.